Welcome back to the Deep Dive, where we take the most dense, high-stakes engineering specifications and, well, we try to distill them into actionable, crystal-clear knowledge.
It's good to be here.
Today, we are undertaking a really ambitious one. We're going straight into the very lifeblood of the future of urban air mobility.
We really are.
We're looking at the electrical nervous system of the P-13 hybrid eVTOL.
And it is a fascinating and, frankly, a really rigorous set of sources we have today. We're looking at the foundational engineering spec and design review for the P-13's entire 800-volt high-voltage system.
The whole thing.
The whole thing. So this covers everything from the DC bus, the power connectors, the high-speed contactors, fuses, the core power conversion units. I mean, in short, we're analyzing the architectural decisions that have to manage a megawatt-class flow of energy. And
the stakes here are, they're almost beyond imagination. This isn't some prototype toy. This is an aircraft aiming for type certification under the SCVTOL enhanced category.
Right, and that's the key.
That means achieving a catastrophic failure rate that is, well, it's statistically negligible. We're talking lower than 1 in a billion flight hours. That's 10 to the minus 9.
10 to the minus 9. That number alone, that single requirement, fundamentally dictates every single component choice and every design decision we are about to discuss.
So it's the North Star for the entire project.
It is the core mandate.
Oh.
And to meet that non-negotiable threshold, the engineering team had to adopt a strategy based on, what we'd call MECE principles, mutually exclusive, collectively exhaustive redundancy, and structured top-down architectural thinking.
Yeah.
They essentially built the system around overcoming 3 fundamental physical barriers that are just inherent to a high-voltage system operating at high altitude.
So before we jump into the parts list, what are those 3 fundamental barriers, the ones that really define the entire design philosophy here?
Okay, so the first barrier is high-altitude insulation. This is a pure physics challenge. It's about maintaining dielectric strength when the atmosphere around you, because of the low pressure, is actively trying to conduct electricity. It's all governed by Paschen's law.
Right.
The second is catastrophic fault containment. So that means designing a rapid, dissimilar defense against a sustained, high-power DC arc fault.
And a DC arc is particularly nasty.
Oh, it's terrifying. Unlike a more forgiving AC arc, it has no zero crossing to self-extinguish, so it just keeps burning, making it terrifyingly efficient at melting through components.
That's the third barrier.
The third is really a market necessity, power conversion density. We're dealing with aircraft, so every single ounce, every gram has to be shed if possible. This requires achieving unprecedented power density and efficiency to make the whole lightweight, high-performance eVTOL concept, economically and physically viable.
So those 3 challenges, that's the lens.
That's the lens through which we have to view every single component selection.
Okay, let's unpack this. We have to start with the foundation. If the goal is 10 to the minus 9 reliability, the architecture itself must be immune to single points of failure.
Exactly. And that's where you begin, from the top down.
So let's get into section 1, the strategic foundation architecture and redundancy.
Exactly. So when you analyze the P-13 system, it operates as a pretty sophisticated series parallel hybrid. You have a P1 generator starter working with the P3 propulsion motors.
And they all meet somewhere.
They all converge on a nominal 800-volt DC bus. And crucially, that bus has to handle a really wide working envelope. We're talking fluctuations between 600 volts and 900 volts.
Why such a big range?
Well, it depends on the state of the system. Are the batteries charging, discharging? Is the generator at peak output? All of those conditions change the bus voltage dynamically.
So how do you prevent that massive power fluctuation, or worse, a sudden short circuit, from taking down the entire aircraft?
You start by designing safety in, not, bolting it on afterwards. The primary structural strategy here is the split bus topology, and it's managed by an intelligent power distribution unit, or PDU.
And this gets back to that MECE principle you mentioned.
It adheres strictly to it. The idea is to ensure every potential failure is isolated into a mutually exclusive domain. It is the architectural cornerstone for achieving that no single failure principle mandated by the enhanced category certification.
Describe that physical split for our listener. What does separating the system right down the middle actually achieve in practice?
Okay, so imagine the aircraft's entire electrical network, all the motors, the batteries, being fundamentally divided. You have a channel A, let's say the left side, and a channel B on the right side.
And this isn't just a software thing.
Oh, no, not at all. They are not just logically separated. They are physically segregated. Channel A has its own dedicated battery pack, its own set of propulsion inverters feeding its own motors.
Yeah.
Channel B is completely independent. The wiring harnesses are run separately, the PDUs are compartmentalized. It's a true physical split.
So if the left side experiences I don't know, a catastrophic short circuit, or if that left side battery goes into thermal runaway.
That event is physically and electrically contained. The right side is completely unaware and remains fully functional.
Wow.
That physical segregation is the strategic basis for fault tolerance. If you lose an entire channel, a major component like an inverter or a whole battery pack, the remaining channel can still maintain enough power and control authority to transition the aircraft to a sustained safety flight mode and execute a controlled landing.
That's what makes that 10 to the -9 target even conceivable.
It's the only way it's conceivable.
But wait, hang on. If they're completely independent, doesn't that create a new vulnerability? Let's say the left battery fails, but the motors on the left wing are still needed to provide the differential thrust for, say, a stable landing in high winds. Now, those motors are just starved of power, even though the right side has plenty.
That is the exact trade-off. It's inherent in any segregated architecture, and it's addressed by the single most strategic piece of hardware in the entire PDU.
Which is?
The crossfeed contactor. This contactor, the switch, normally remains open during all phases of flight. That's its default state, preserving the independence of the two channels.
But the moment you have a partial failure.
The Vehicle Control Unit, the VCU, it analyzes the failure mode in real time. If it determines that the failure is contained, for instance, just the loss of a battery source on Channel A, but Channel A's inverters and motors are still perfectly healthy, it can intelligently command that crossfeed contactor to close.
So it's effectively creating an emergency bridge.
Correct. It allows the healthy channel, Channel B in our example, to supply power across to the critically loaded components on the failed side.
It's not full power, I assume.
No, it doesn't mean the failed side operates at full power, but it ensures enough power flow to maintain thrust vectoring, stability, and critical control surfaces. It enables the completion of the flight envelope and a safe, stable landing. It transforms a total loss of power on one side into a graceful degradation scenario.
That makes perfect sense. Independence for safety, but a controlled bridge for survivability. Okay, now let's talk about the sensitive brain of the aircraft. How do they step down that enormous 800V bus power to the fragile 28V needed for the flight control computer, all the sensors, and the avionics?
That is the role of the HVDCC converters, the high-voltage DC to DC converters. You can think of them as the guardians between the high-power systems and the low-power control systems.
Their function sounds simple enough.
The function is simple. Stable, reliable conversion from 800 VDC down to 28 VDC. But their design is incredibly complex because of the safety requirements.
The specification lists galvanic isolation as a completely non-negotiable feature. Why is that physical separation so fundamentally important, especially when modern electronics can often handle high common mode voltage?
Because we're not dealing with normal conditions, we're dealing with extreme transients. Galvanic isolation, which is usually achieved with a transformer or maybe optical coupling, means there is no metallic direct electrical path connecting the 800V side to the 28V control side.
And that's crucial because...
Two big reasons. First, it eliminates the risk of high voltage surges, maybe from a massive short or even a lightning strike, propagating directly into the sensitive low voltage electronics like the flight control computer, the FCC.
You'd fry the brain.
Instantly. Second, if you have an insulation fault on the 800V side, the 28V system remains entirely protected. It prevents a simple insulation breakdown from leading to the catastrophic loss of aircraft control.
So it's the electrical equivalent of an impervious firewall.
Absolutely. Now, you also noted the specification requires these converters to be bidirectional. Why would a system that's designed to step voltage down also need the ability to push power back up?
I would assume it had something to do with maintenance or maybe startup reliability, given that 800V systems need a really careful initialization sequence.
You nailed it. It's for operational robustness, specifically for the pre-charge sequence. High-voltage buses have these massive capacitors that need to be slowly and smoothly charged before you close the main high-power contactors.
Right, if you just slam them shut.
You get a huge inrush current that can damage the system, weld the contactor contacts. The bidirectional DC-DC allows the low-voltage 28V backup battery system to push a small controlled current back up into the 800V bus, executing a smooth pre-charge.
That significantly enhances startup reliability, especially if you're launching from a cold-soaked condition on a winter morning.
And finally, that 10 to the minus 9 safety target means redundancy has to be built into the DC-DC unit itself. The requirement mandates a multi-phase, parallel, redundant architecture.
So the DC-DC isn't just one black box.
No, it's several smaller, identical converters all working in parallel. If one of those units fails, say a semiconductor fault in a single phase, the remaining units must immediately and seamlessly take over the full load. The specification states the system must sustain at least 70% of the required 28V supply, even after a single channel failure.
So the FCC never starves for power. Not for a microsecond.
Never. It's a beautifully layered approach. The architecture provides redundancy at the macro level with the split bus, and then the components provide redundancy at the micro level, like these DC-DC parallel channels.
Okay, now that we understand the strategic foundation, let's move into the truly challenging physical environment these individual components have to survive in.
Right. This is where we shift from architecture to applied physics.
Section 2. Component selection, overcoming physical extremes.
We need components that don't just handle 800V and high current. They must survive an environment dictated by high altitude and extreme temperature swings, often at the same time. The first engineering fight is against nature itself. High altitude insulation, or the notorious problem presented by Paschen's law.
Let's spend some time on this because it's where standard electrical engineering really breaks down in aviation. Explain, from an engineering perspective, what Paschen's law dictates in the context of an AV2 flying at, say, 25,000 feet.
Okay. So Paschen's law describes the voltage that's required to cause an electrical breakdown, a spark, across a gap in a gas. And the breakdown voltage is a function of the product of the gas pressure and the distance of that gap.
And it's not a simple linear relationship.
Not at all. That's the key. It's counterintuitive. If you look at the Paschen curve, the breakdown voltage is not lowest at sea level, and it's not lowest in a perfect vacuum either. It hits a crucial minimum, a trough, at an intermediate low pressure.
And what does that intermediate low pressure correspond to in aviation terms?
It corresponds precisely to the cruising altitudes of many aircraft, roughly between 20,000 and 35,000 feet. At these altitudes, the air density has decreased just enough to maximize what we call the mean free path of electrons.
Meaning they travel farther before hitting something.
Exactly. They travel farther before colliding with an air molecule, so they gain more energy, enough to cause a runaway ionization chain reaction. This environment actively invites ionization, dramatically increasing the risk of corona discharge and partial discharge, or PD.
And the risk of PD is that it's a slow, silent erosion of the insulating material around the conductors. It just eats away at it over time.
It's an insidious failure mode. So how do the component engineers fight a physical phenomenon that is driven by altitude itself?
That's the question.
They fight it by demanding massive safety margins and really advanced material science. For the high-voltage connections, which are the critical weak points, they specified the Amphenol HV38999 Raptor connector. This isn't just a tough military-style connector, it's a specialty item.
And what makes it so special in this context?
It is specifically validated to be PD-free at 50,000 feet. Now think about the design margin this provides. If your operational ceiling is 25,000 feet, certifying it to double that altitude ensures that the system is operating far, far outside the most dangerous region of that Paschen curve.
And that's a hard requirement.
It's a hard requirement. This certification proves compliance with SAE AR 6127, which requires partial discharge to be less than 10 picocoulombs. That is a microscopic amount of electrical discharge. If the connector fails that vacuum chamber test, the aircraft simply doesn't get certified. End of story.
That is a direct link between pure physics and component selection. Okay, let's move to the contactors, the heavy-duty switches. We talked about how an 800 VDC arc is incredibly difficult to extinguish because it never naturally cycles off. Low pressure only makes that problem worse.
Oh, it compounds it terribly. In a traditional open-air contactor, the low oxygen and low pressure make arc suppression almost impossible. The plasma just sustains itself indefinitely. The P13 solution specifies the TE Connectivity Kilovac series, and it demands a hermetic ceramic sealed design.
So they just bypass the ambient atmosphere entirely.
They do. The critical switching contacts are sealed inside a robust ceramic housing that is then filled with a specific inert gas, often sulfur hexafluoride, SF6, or maybe pressurized nitrogen. This artificial atmosphere inside provides a highly effective, stable medium for arc suppression.
Meaning the contactor's performance doesn't change with altitude.
Its ability to safely break massive DC current is entirely unaffected by external altitude or air density. It's basically a non-atmospheric environment for a switching device that has to operate in the atmosphere.
Brilliant. Now, let's tackle that third challenge. Power conversion density. Moving away from old, heavy equipment is critical for eVTOLs to even be viable. What kind of weight reduction are they aiming for, and what's the core technology that allows that?
The mandate is really ambitious. They need to achieve a power-to-weight ratio exceeding 2.5 kilowatts per kilogram. That leads to an integrated weight reduction of around 45% compared to older silicon-based industrial power platforms.
And that's a huge gain.
It's a massive gain, and it's only possible because of the transition to wide bandgap semiconductors, namely silicon carbide, CS, and to a lesser extent, gallium nitride, GaN.
So why are CSEC devices so much better for power density than traditional silicon? What's the magic there?
They can switch on and off far, far faster than traditional silicon devices. We're talking hundreds of kilohertz. This high-frequency switching allows the engineers to dramatically shrink the size, and therefore the weight, of all the passive components, the transformers, inductors, capacitors.
Smaller parts, less weight.
Less bulk, less weight, higher power throughput. The trade-off, however, is electromagnetic noise, which is a big problem we'll have to address later.
So let's look at the HVDC-DC conversion unit where these materials are actually being applied. The spec calls out Vickers BCM-DCM chip modules.
The Vickers modules are key because they hit that greater than 2.5 kiloquino kilocalorie density target. But the real engineering insight here is their utilization of the sine amplitude converter, or SAC topology.
And what's special about that topology?
It operates at very high frequencies, but it does so using a naturally soft switching technique. This makes it inherently highly efficient. We're talking over 98.5% efficiency. And crucially, it produces inherently low electromagnetic interference, or EMI.
So by choosing a clever topology, they partially mitigate the noise problem that CSE inherently introduces right at the source. That simplifies the challenge of meeting the DO-160G EMC standards later on.
Exactly. They're solving two problems with one component choice. It's elegant. Finally, we have the DC link capacitors. These are they're the unsung heroes of the power path, really. They stabilize the 800V bus against the massive voltage ripple created by the CNC inverters.
And the specification is extremely clear here. It says to use metallized polypropylene film capacitors and to absolutely, under no circumstances, use aluminum electrolytic capacitors. Why such a firm prohibition?
This is a critical safety distinction, and it's tied directly to the operational envelope of the aircraft. As we discussed, the aircraft has to operate down to minus 55 degrees Celsius.
And aluminum electrolytics use a liquid.
They use a liquid electrolyte. And when that electrolyte approaches freezing, its conductivity just plummets, and its equivalent series resistance, the ESR, its internal inefficiency skyrockets. The capacitor loses its ability to filter, the bus voltage destabilizes, and you risk a power quality failure. Not to mention the risk of the chemical just leaking or the can rupturing.
So the environment itself turns a simple capacitor into a major point of failure.
Whereas the film capacitor, which is made of polymer film and metallization, has no liquid components. It maintains stable characteristics across the entire required temperature range. But its ultimate advantage, and the real reason it's chosen, is a passive safety feature you mentioned, the self-healing property.
Can you elaborate on that? It sounds like a fantastic, almost futuristic material property.
It's brilliant passive engineering. So if a voltage spike causes a microscopic fault, a tiny pinhole in the dielectric film, the energy from that fault is concentrated at that one tiny point. This energy instantly vaporizes the incredibly thin metallic coating, the electrode right around that pinhole, effectively isolating the damage. The insulation is immediately restored, and the capacitor continues to function with only a negligible loss of capacity.
So it fixes itself.
It's a passive, instantaneous repair mechanism, and that's why they are selected for high reliability aerospace use over any liquid-based capacitor. It builds reliability right into the material composition itself.
That means the component can survive minor electrical stress events that would instantly destroy an aluminum capacitor. It's an inherent layer of redundancy right there.
Huh.
Okay, so we've covered prevention through architecture and prevention through component selection. Now, let's discuss what happens when the inevitable severe fault, the thing that only happens once in a billion flight hours, actually occurs. Section 3, the Intelligent Defense System Fault Containment. Here's where it gets really interesting, how they stop a massive 800V fault in mere microseconds. We're talking about preventing an uncontrolled DC arc from becoming a catastrophe and escalating into something like a battery thermal runaway.
This requires a multi-layered approach. The sources call it a system of dissimilar redundancy. You cannot rely on a single mechanism for a 10 to the minus 9 safety mandate. The failure propagation speed in an 800V bus is nearly instantaneous.
So you need layers of defense.
You need layers, and each has to use a different physical principle to catch the fault. Layer 1 is the speedster. It's the electronic guardian.
And that is?
That is the solid-state power controller, or SSPC. Think DDC, SSPC modules. This is an electronic breaker. It leverages semiconductor technology, not mechanical movement, to interrupt the current flow. And its response time as well, it's ultra-fast, less than 10 microseconds.
10 microseconds. That's 1/100th of a millisecond. Why the maniacal obsession with speed?
Because the primary purpose of the SSPC is to shield the most expensive and sensitive equipment on the bus, specifically those SISTA power modules, from their own sudden fault current. SIC devices are extremely sensitive to brief, high-energy current spikes. The SSPC must trip and completely sever the circuit before the current reaches a level that causes permanent physical damage to the SIC module junction. It's the rapid, resettable first line of defense.
But if that electronic defense fails, or if the fault is so enormous and unexpected that you need an ultimate, non-resettable solution, that brings us to layer 2, the decidedly analog defense.
That's the physical airbag of the system.
Yeah.
The pyrotechnic fuse, or pyro-fuse. This is the last line of defense, designed to contain truly catastrophic, unmanageable faults.
Still fast, though.
Oh, its response time is still blindingly fast, less than 1 millisecond. But the pyro-fuse is actively triggered by the VCU when an extreme, uncontrolled event is detected. Something like a ground fault that the SSPC failed to clear, or conditions that strongly indicate an imminent battery thermal runaway event.
I want to focus on the difference here. This isn't a normal fuse where a wire melts. It uses a pyrotechnic charge to physically sever the connection. It's a controlled explosion inside the system.
It is a deliberate, irreversible action. The physical separation that's achieved by that pyrotechnic charge creates an immediate, permanent, and absolutely guaranteed isolation barrier. It is the ultimate containment strategy.
And it ensures the battery can't keep feeding the fire.
It ensures that the massive energy source, the battery, cannot continue to fuel a fault, preventing the spread of disaster to the rest of the airframe. The design review really emphasizes the necessity of coordinating this timing triad. You have the SSPC at less than 10 microseconds, the pyro-fuse at less than a millisecond, and then the main mechanical contactor opening at around 10 to 15 milliseconds. This hierarchy is rigorously tested.
It's just fascinating how the most cutting-edge electronic system relies on an ultimate, almost brutal physical severance mechanism. Now, shifting focus from hardware protection to human safety, ground crew safety is paramount.
Absolutely. We are dealing with 800 volts, so even when the system is shut down, those massive DC link capacitors can retain a potentially lethal charge for a long time. The system must incorporate an active discharge function.
And there's a hard rule for that.
The rule for ground crew protection is clear. Upon system shutdown, or if the high voltage interlock loop is broken, the DC link voltage must be dissipated below the 60-volt safety threshold within 5 seconds. This completely eliminates the residual shock risk.
And what about physical contact safety? Ensuring nobody can accidentally touch a live or potentially live conductor during maintenance.
That's all covered by the IP, or ingress protection requirements. The specification mandates 2 distinct levels. When high-voltage components are disconnected, they have to meet IP2XXB.
Which means?
It means they're finger-safe. It prevents access to any conductors larger than 12.5 millimeters in diameter. When they are connected and locked, they must achieve IP67. That's full protection against dust ingress and the capability to survive short-term immersion in water. This guarantees environmental and contact safety across all phases of maintenance and operation.
Finally, let's discuss the single most important safety check for connectors. The high-voltage interlock loop, the HVIL. This is all about preventing a critical safety violation, unplugging a high-voltage connector while it's still live.
The HVIL is a low-voltage sensing circuit. It runs through dedicated pins in every single high-voltage connector. It acts as a continuous watchdog, constantly monitoring the physical integrity of the entire high-voltage system connection path. But the genius is in the mechanical design, which is built around the principle of last make, first break.
Let's break down that mechanical genius. How does that work?
The HVIL signal pins are engineered to be physically slightly shorter than the main power pins. So when you connect the plug, the robust power pins make contact first, and the short HVIL pins make contact last.
So the power connection is only established after the control loop is complete.
Right. And conversely, when you disconnect, the short HVIL pins break contact first before the long power pins have physically separated.
Which ensures the VCU registers the connection integrity break before the dangerous power separation happens.
Exactly. The VCU is alerted before the massive 800V bus is exposed to a potential arc. The total system response time from detecting that HVIL break to the main contactor's cutting power has to be lightning fast. Ideally less than 15 milliseconds, and absolutely mandated to be less than 50 milliseconds.
But the true lesson here isn't just the speed.
No, the real engineering lesson is the philosophical priority that underlies the HVI logic. It's the reliance on hardware priority over software.
Explain that.
The VCU cannot wait for an operating system to boot up or for a software loop to execute. The HVIL detection logic must be hardwired, a direct circuit-based system, or may be handled by dedicated non-software dependent FPGAs. Software is only used for logging and status reporting. The core shutoff logic must bypass the main operating system to eliminate any risk of latency, deadlocks, or software bugs interfering with the core safety shutdown.
That is a profound statement about safety engineering in a world of increasing software complexity. You're trusting the fastest, most reliable thing there is, the speed of electrons in a circuit over the reliability of code.
At the end of the day, for core safety, physics has to win.
Section 4. Insulating the system integrity monitoring. Shifting to continuous preventative measures, we have to address the grounding strategy and how the system maintains insulation integrity throughout the airframe structure.
Right.
The P-13 utilizes a floating ground strategy, which is known as an IT grounding system. This is non-standard compared to many automotive EVs that use a solid ground system.
That distinction is absolutely critical for flight safety. In an IT system, both the HV Plus and the HV lines are electrically isolated or floating from the aircraft chassis ground. They are not intentionally connected to the metal structure in any way.
And the massive safety advantage this gives you is what?
It buys you time. If, due to insulation degradation, one pole, let's say HV Plus, vaults and makes contact with the airframe's metal structure, you have not created a short circuit. You've only grounded that one pole. Because the system is floating, the current has no path to return to the battery through the structure, so the system can continue to operate, at least temporarily. This allows the pilot to recognize the failure and execute a controlled, safe landing. It fulfills that graceful degradation requirement we talked about.
That is crucial. So a single insulation fault is not a catastrophic event. But if it's floating, how do you even detect that first insulation failure before the second pole-to-pole fault occurs, which would be catastrophic?
That is the essential job of the Insulation Monitoring Device, or IMD. The IMD continuously injects a low-level sensing signal between the HV bus, both poles, and the aircraft structure, the ground. It's constantly calculating the insulation resistance, acting as the system's electronic health checker, second by second.
And the specification defines 2 precise quantitative safety tripwires based on that resistance level. This gives the operator time to react.
Precisely. The first tier is the warning level. If the resistance drops below 500 ohms per volt, so for an 800V system that's 400 kiloohms, this indicates early insulation degradation. This is purely a maintenance warning. It's flagged to the VCU. The system is safe to continue operation, but maintenance must be scheduled immediately.
And the second tier, the emergency level.
That is the hazardous failure level. If that resistance drops below 100 ohms per volt, so 80 kiloohms, it signals a severe insulation breakdown. This is a severe threat because now a second independent fault on the other pole, HV, would result in a catastrophic dead short circuit right through the airframe.
And at that point?
At that point, the PDU must immediately isolate the high voltage source by opening the main contactor, and the pilot must initiate an immediate controlled landing procedure. The difference between 500 ohms per volt and 100 ohms per volt is the engineering distinction between a maintenance issue and an operational emergency.
All of this integrity monitoring relies on the quality of the physical conductors and their insulation. We talked about Paschen's law and the connectors. What about the actual wiring harness and the bus bars inside the PDU?
For the wiring harness insulation, the material specification is paramount. They mandate anti-corona materials like PEEK or polyon. Standard aerospace insulation just won't cut it at these voltages and altitudes. These materials are chosen specifically because they resist the erosion caused by partial discharge and low-pressure environments. They're validated for performance well above 10,000 feet.
And let's revisit that EMI problem introduced by the high-speed C switching. That noise has to be contained. How do they physically ensure the wiring harness isn't broadcasting interference across the entire airframe?
They require incredibly robust shielding. The harness must use double braid shielding with a coverage greater than 90%. But more importantly, the shielding must terminate cleanly via a 360-degree connection to the airframe ground at every single termination point.
So no gaps.
No gaps. This unbroken, continuous shield acts as a Faraday cage, suppressing the extreme high-frequency noise generated by the SISIC inverters. This is what ensures compliance with RTCA DO-160G Section 21 for emissions.
So if the shielding isn't perfect, the sensitive GPS, communication, or even the flight control systems could be affected.
Precisely. That EMI could manifest as anything from simple static on the radio to corrupted signals in the flight control computer, which is completely unacceptable for a certified aircraft. And the mitigation for that starts right where the power is distributed, the DC bus bar inside the PDU.
What's the engineering solution there? How is that designed?
They require a laminated busbar design. This means the HV plus and HV copper layers are stacked extremely tightly together, separated only by a very thin layer of dielectric insulation. This tight parallel coupling minimizes the stray inductance, the magnetic energy that gets stored in the power path, down to less than 20 nanohenries.
Why is that nanoscopic value so crucial?
Well, every time a SEEK device switches in microseconds, it creates a massive rate of change of current, or DID. Any stray inductance in the path, even tiny amounts, reacts violently to this change by generating a huge destructive voltage spike. The formula is V equals L times DID.
So by minimizing L, the inductance...
By minimizing L through lamination, they minimize those voltage spikes right at the source. This protects the semiconductors themselves and reduces the amount of noise that needs to be filtered downstream. It's a really elegant solution that manages the complexity that 6E brings to the table.
The level of physical detail here, from the material science of the film caps to the precise geometry of the bus bars, it's just stunning. But as we discussed, a design on paper is not a certification. You need proof.
Cold, hard, documented proof.
Section 5. Verification and compliance. The proof.
To satisfy EASA requirements, every single requirement we've discussed has to be translated into a rigorously regulated and documented test program. This is what leads to type certification. The design is robust, but the evidence must be undeniable.
Let's start with the toughest physical test. Proving that high-altitude electrical integrity. That's the partial discharge test. Compliance with SAE ARR 6127 for high-altitude insulation is proven in a specialized vacuum chamber. This chamber simulates low pressure, often pushing to the equivalent of 30,000 feet or even higher, while the component, the cables, the connectors, is energized at 1.5 times the working voltage. So for an 800V system, that's 1200 VDC.
And what are they looking for inside that chamber?
They are listening and measuring for that silent killer, the partial discharge. They have sensors that can detect those tiny sparks. If the measured discharge exceeds 10 picocoulombs, the component fails, period. This is a critical pass-fail metric. It is the direct physical proof that the selected peak insulation and the amphenol connectors will not degrade and arc over at altitude. Moving to electronic noise, the EMCMI compliance under RTCA DO-160G. What is the scope of testing there? It must be huge.
It is. Verification covers three major areas. First, high-intensity radiated fields, HIRF, which ensures the aircraft's systems can operate near powerful radio sources like a broadcast tower. Then, conducted and radiated emissions, ensuring the 800V system's own noise doesn't interfere with the aircraft's own sensitive systems. And crucially, lightning-induced transients.
Oh, they zap it.
They zap it. They have to prove that a simulated lightning strike does not corrupt the data lines or destroy the 28V control systems. This is where features like the galvanic isolation in the DC-DC converters really prove their worth.
And now let's talk about the absolute ultimate test for the fault containment system, the SSPC, the pyro-fuse, the contactors. It's called the copper bird integration test. This sounds less like a lab test and more like a physical demonstration of violence.
It absolutely is. This test verifies short-circuit protection as required by EASA SCE 19. You cannot simulate a catastrophic DC arc fault with software alone and get certification sign-off from EASA. They won't accept it.
So what is the copper?
The Copper Bird is a full-scale ground test platform. It's constructed using the actual PDU, the actual batteries, the exact wiring harness lengths, but it's connected to massive, non-flight-rated dummy load banks and specialized fault injection hardware.
Why is this expensive physical setup necessary? Why can't they just use mathematical models?
Because the goal is to observe the real physical reaction of the system to a deliberate, hard short circuit. They physically inject faults line-to-line shorts, line-to-ground shorts, and use high-speed measurement equipment to verify two critical things.
Which are?
First, that the SSPC trips within its 10 microsecond window. And second, that if the fault persists, the pyro-fuse triggers at exactly the right point in time and successfully completely cuts off the energy flow. They need to prove the containment devices can survive and contain the enormous energy pulse that results from short-circuiting an 800-volt megawatt class battery.
The coordination verification is the key, right?
It is. The test validates the entire hierarchy of defense. It proves that the system can isolate massive energy in milliseconds, exactly as designed. If the pyro-fuse fires too late, the busbar might literally vaporize. If it fires too early, the system loses a critical component unnecessarily during a manageable fault.
Beyond electrical performance, we have the environmental gauntlet every single component has to run.
That's the RTCA DO-160G environmental durability testing. Components must pass rigorous tests for structural integrity and electrical performance under extreme mechanical and thermal stress. This includes vibration profiles, simulating continuous flight, and temperature cycling from the extreme cold of -55°C.
Making sure those film caps don't fail.
Making sure the seals and capacitors don't fail, exactly, all the way up to +70°C to ensure the thermal management system is sufficient at the hottest operational point.
Can you give us some hard, measurable acceptance criteria that really highlight the precision demanded by this specification?
Certainly. The requirements are extremely tight. For DC-DC performance, the conversion efficiency must be greater than 96% at 50% load. For bus stability, during a sudden, massive motor demand change, the voltage transient on the DC bus has to be less than 10%, and the recovery time must be under 200 milliseconds.
That's incredibly fast recovery.
And for integrity, the dielectric withstand, or HIPOT test, must confirm the insulation can hold 2800 VDC for 1 minute, even when that test is conducted in a low-pressure, high-altitude simulation.
And one detail that speaks volumes about the commercial operational lifespan: the connector reliability requirement.
That's the fleet-wide robustness check. The collector's contact resistance, which is a measure of the efficiency of the power transfer, must increase by less than 10% after 10,000 mating cycles and full vibration testing.
10,000.
This speaks to the need for a system that can be reliably connected, disconnected, and reconnected thousands of times over the vehicle's intended 10-year lifespan without any significant degradation.
It's clear the design is mature, but the review identified some critical risks that have to be addressed immediately before certification is even feasible. So what are the engineering team's immediate concerns?
Right. This is Section 6, Identified Risks and Future Action Items.
Where the theory meets reality.
Exactly. The review concluded the architecture is sound, but certification hangs on demonstrating control over 3 specific real-world execution risks. This is the difference between an academic success and a certifiable flight vehicle.
Let's start with that crucial high-altitude risk, the partial discharge problem.
Okay, so risk 1. Manufacturing variability in partial discharge. While the specialized connectors are certified PD-free at 50,000 feet, the risk now shifts to the production environment. Manufacturing processes introduce small, inevitable variations.
Like what?
A microscopic burr left on a bus bar during cutting, an inconsistent thickness of conformal coating on a solder joint, or a slight imperfection in the wire stripping process.
And at high altitude, these minute manufacturing defects become new points of ionization and partial discharge.
Exactly. They become low-pressure lightning rods. The critical recommendation here is that the engineering team cannot, under any circumstances, rely on spot checks or type certification alone. They must implement 100% partial discharge testing for every single production PDU and every critical high-voltage wiring harness before it is installed on an aircraft.
So it moves from a design issue to a production quality control gateway.
It has to. Every unit must be screened.
Moving to the containment system, the coordination of the SSPC and the pyro-fuse, what's the risk there?
Risk 2, protection coordination blind spots. So we know the SSPC handles fast, hard faults, and the pyro-fuse handles the massive, severe faults. The risk exists in the middle ground, what engineers call boundary faults.
Low-rising faults.
Exactly. These are slow-rising overload conditions with a low DIT. If the current rises slowly, the SSPC might interpret it as a permissible temporary overload rather than a hard short, and it could stay closed for too long. At the same time, the fault might not be severe enough to hit the immediate activation threshold of the pyro-fuse,
leaving the system exposed in a failure mode that the architecture wasn't fully designed to cover. A blind spot.
Precisely. The solution is to expand the scope of the copper bird test. They must specifically verify the component responses under varying fault current rates. They have to test the system with intentionally slower DIT profiles to map out the complete protection coordination curve. They need to prove there are no gaps where the fault could damage equipment before it's finally cleared by the ultimate defense.
And the third risk deals with the silent, insidious threat to component lifespan.
Risk 3. Thermal management and lifespan. The concern is the lack of a defined thermal margin when you combine extreme operational conditions. For example, operating at the maximum ambient temperature of plus 70 Celsius, while simultaneously being at high altitude, which, as we know, reduces the efficiency of any air-based cooling systems due to the low air density.
And as we discussed earlier, this directly threatens the longevity of the DC-link film capacitors because of the internal heat generated by ripple current.
Yes. High internal temperature accelerates chemical and physical degradation exponentially. It slashes the guaranteed lifespan. The recommendation requires 2 specific actions. First, detailed, coupled computational fluid dynamics, or CFD analysis, to accurately model the heat flow under these worst-case scenarios.
And second.
And second, critically, mandatory temperature-altitude combined cycle testing in environmental chambers. They have to prove thermal stability at the worst-case operational point to guarantee the components will meet their 10-year lifespan target in the real world.
The overall conclusion is confidence, provided the evidence is gathered. So what are the 3 non-negotiable immediate action items, the critical path items that the team has to tackle starting today?
The path to ASA certification is clear. First, highest priority. Immediately launch and finalize the high vacuum chamber partial discharge test plan. This is the core physical evidence they need to prove high altitude airworthiness. Without it, nothing else matters.
Number 2.
Second, supply chain finalization. Those long-lead critical components, the Amphenol HV38999 connectors, the Vickr DC-DC modules, they need to have their supply chains locked down and qualified immediately to ensure consistency and prevent delays in production.
And finally.
Third, integration platform acceleration. They need to accelerate the construction and commissioning of the Copperbird integration platform. Testing the system-level fault injection and coordination is now the gatekeeper for system integration and final performance sign-off.
This entire deep dive just shows that the glamorous vision of the eVTOL future is actually built on a relentless, measured commitment to rigorous testing and, well, microscopic material science.
That's a perfect way to put it.
So to wrap up in our outro, we have spent the last 40 minutes or so traversing the electrical nervous systems of the P13 eVTOL. And the main takeaway for me is that the 800V system is not just an efficiently lightweight power path, saving an estimated 45% harness weight. It is a multi-layered, heavily regulated safety shield.
Absolutely. The design philosophy is a masterclass in risk mitigation. You see it everywhere. Components selected specifically because they negate a physical flaw in the environment, like the inert gas-sealed contactors to fight vacuum arcing, and the film capacitors chosen specifically for their passive, inherent self-healing capability. They didn't just meet standards. They built a system designed to exceed the physical limitations of commercial aerospace.
So what does this all mean for you, whether you are preparing for a technical meeting on this or just curious about the future of aviation? It means the success of urban air mobility relies less on the flashy industrial design and much more on the unseen battle against physical forces.
The integrity of the air gap between 2 conductors at 25,000 feet.
And the ability to sever a dangerous current in a handful of milliseconds.
And that connects back to the core philosophical safeguard that's inherent in the design. We discussed how this system relies on that non-negotiable principle of hardware priority over software logic for critical safety functions, especially the HVIL cutoff. Given the ever-increasing complexity and potential latency in autonomous flight control software, that physical, circuit-based redundancy is the ultimate philosophical choice.
Which raises one final provocative thought for you to explore. In this cutting-edge megawatt-class power system, a system that utilizes the fastest silicon carbide electronics, complex controllers, and high-speed software, why do the engineers ultimately protect the entire vehicle with the oldest, most reliable safety mechanism known to engineering?
A controlled physical explosion, the pyro-fuse.
Why?
I think it's the ultimate recognition of physics. When you are faced with a catastrophic, unrecoverable failure, the only guarantee is the definitive physical severance of the energy path. Software can fail, electronics can fail, but a physical gap is a physical gap.
That's a powerful way to end this deep dive into the high-voltage nervous system of the P13 eVTOL. We hope you found the journey insightful.
Thank you for joining us.
See you next time.